Hello and welcome to the video recap lectures for the Maths and Computation for Physics first year module. These short videos are going to be designed to recap and consolidate your knowledge gained after having attended the sessions and worked through the materials in each of the sessions. Learning computing is absolutely something that you have to be able to work through yourself, and in the sessions you'll be guided through various exercises designed to help you understand the power of computing in physics. Only after you've got your hands dirty with these exercises and been able to ask the teaching assistants for help if you get stuck, then you should watch these videos to make sure that you get an idea of what we were trying to achieve in the sessions and answer any final questions that you may have. So in the sessions, we're going to be trying to learn a programming language called Python. Python's an incredibly powerful language that's been used across a very diverse range of applications, from web development all the way to high-performance numerical simulation. So on top of Python, we're also going to be learning Python within something called Jupyter notebooks. Now these are notebooks that are divided into cells that can contain either text or code snippets written in Python. So it allows you to see text and Python code together at the same time, and our lecture notes are going to be written in these Jupyter notebooks. So the first thing we need to be able to do is to get hold of these Jupyter notebooks. And all of these notebooks are going to be found on Keats. So Keats is the e-learning environment that's used within King's. So if we go to Keats, the web address is keats.kcl.ac.uk. If we go there, you should have enrolled in the 4CCP 1300 module, which is the Mathematics and Computation for Physics module. If you can't see this on your Keats dashboard, you need to search for it and enroll in it. After you've done that, you click on it and you go down to the Computational Laboratory. If you expand this, you will see the Computational Lab Session 1. If you click on this, you will have access to the materials for that Computational Lab session. And there are two files, and both of these need to be downloaded and put into the same folder. So the easiest way to do that is to right-click on each of the files, go to Save Link As, and then find a place in your computer that you want to save it locally. So I might want to install it to save it in Work, and then I might want a new folder which could be Computational Lab Session 1. As you can see, I'm actually doing this on a Mac. In the sessions, you'll be doing this on Linux workstations. You can set this up on your laptops or your computers at home as well. So if I create this folder, then I can save this, what's called an IPYNB, which stands for IPython Notebook, to that folder, and I will do the same for tutor.py. There will be a tutor.py for every single computational lab session along with a notebook. So you need to save those both to the same folder. Okay, those are the materials. What we now need to do is we need to open a Jupyter environment. Right? And to do this, the easiest way is to actually go to something that you may not have used before, which is the terminal. You can normally see this on any of the drop-down menus that you have, both on the Linux computers in your computational laboratory sessions, or if you have a Mac, they should be available. It's a bit more difficult in Windows, but it can also be done in Windows. So if you click on Terminal, you end up with a text interface like this, and we type Jupyter Notebook. Once we do this, it should open up a tab or a web browser, and then you have access to your computer. You need to then navigate through the file system in order to find where you downloaded the IPython notebook. So I did that in Documents, and I think I went into Work, and Computational Lab Session 1. If I click on that, I have the tutor.py and the Comp Session 1 IPython notebook. I click on the Comp Session 1 IPython notebook, that opens up another tab, and then I have access to the Jupyter notebook in its entirety. So these are the notes for the first session. The first thing that needs to be done, I'm not going to read through these notes, but I'm just going to briefly summarize what the learning outcomes should have been from the first session. The first thing we want to do is get comfortable with the idea of Jupyter and this notebook style environment. So many computational programs are just written in one long file in an editor, and then they're run. But we wanted to be able to have text so that we could provide detailed instruction within each of the sessions, along with bits of code that can be run, such as this here. So the Jupyter notebooks are divided into cells. Now you can see the cell is denoted by this border here, and the fact that I've got a blue bar down the left hand side of the cell denotes that this cell has been selected, right? Each of the cells can be selected, but they can also be put into an editable state, right? Once they're in an editable state, they will actually have a green border. So if I turn it to an editable state, I can do that by double-clicking on any of the cells. If I double-click on the cell, you'll see it changes the text, and it now has a green border around the cell. Remove that bar. Now the cells are divided into two different types. They can be text-based cells, where you insert text, and they can be code cells. Now each of the cells can be run, right? When you run a text-based cell, then it converts it into a nicely formatted state, right? And if I go back to the editable state with the green border, I run the cell by going up and pressing this run button here. Alternatively, I can use a keyboard shortcut, which is Shift and Enter, right? There are lots of different things that we can do in cells. In the text cells, we know it's a text cell because it is denoted as markdown here. If I want to create a new cell, I can press the plus button on the toolbar here, and then it will create a new cell below the cell that I've just been editing. Note that this has a little in prompt here. That's because it is expecting, and by default it is a cell expecting code to run. I can change this by going to cell and changing cell type to markdown, and markdown is the text style that will be used for the cells. So I can click and change that to markdown. The prompt goes and I can type in text. Once I've done this, it's still in an editable format denoted by the green border. I can press Shift and Enter, and it will render that text cell into a presentable fashion. Now, the format is markdown for these text cells, and there are lots of other things you can do for them. I can put in links, I can put in pictures, I can put in equations, and I can put in lists, and I can do much more. So this is a format called Markdown, and there are a number of different links available for simple tutorials for understanding how to write different types of text and format it in different ways within Markdown cells. So this is just a very simple text editor, essentially. So I can have different cells for text. I can also delete the cells by selecting them and pressing D twice. I can also copy and paste cells by selecting them with the blue bar. I can press C, that will copy them, and then I can press V, which will paste them. I can then delete them again. So you should make sure that you're comfortable with being able to move around the Jupyter notebook, selecting cells with the blue bar down the side, double clicking on them to turn them into an editable state, changing them, for instance, by adding your name to the title, and then rendering them by running the cell or pressing Shift and Enter. So I want to encourage all of you to feel free to annotate these notes that are distributed with each session, to add your own information and reminders things that you didn't understand, add additional cells with text in them so that you can make the notes your own and so they can be your own personal reference for what you've learnt during the course. In addition, the final report at the end of the module, at the end of both terms, is going to be in the form of a Jupyter notebook. And so that will involve then you creating both text, equations, figures, and code all within the same file. So from here, we should start thinking about Python itself. So the first thing we want to do is we want to create a new cell. And this time we don't want to change its type from code to a text cell in Markdown. We want to remain as a code cell. So the first thing we want to learn about is variables and assignment. In programming languages, you don't want to work with bare numbers, otherwise you simply have a calculator. What you might want to do instead is assign values to particular variable names that are denoted with text expressions. For instance, I might want to say x equals 5. So what's that doing? It's saying that I want the variable denoted by x to be assigned the value of 5. Okay, so that hasn't done anything so far, but I can print out what that value is in the following way. This is the statement. So this little snippet of code will be evaluated one line at a time. The first line will tell the computer that it needs to create a variable denoted by x, and it needs to assign the value of 5 to that variable. So the equals sign means that there is an assignment of the right-hand side of the equation to the variable given on the left-hand side of the equation. The second line tells us to print out the value of that variable. So again, we want to run this cell in order for it to run the code. Right? We can click on the run, and that will give us an output. It will print the value 5, which is what we expected. We can do other things as well. We can then say things like x equals x plus 5. So what do we expect that to do? Well, it will evaluate what the value is on the right-hand side of the equation, and then that equals means that there will be an assignment of that value to the variable on the left-hand side of the equation. So we start off with the current value of x, which we already know is 5. We will add 5 to it, and we will assign it to the variable x. So it will overwrite its previous value and assign it a new one, which we expect to be 10. If we evaluate that, that is exactly what we get. We get 5 and then we get 10. Should be pointed out that in Jupyter Notebooks, you will always retain the values of any variables that are created in one cell for subsequent cells. So for instance, if I create a new cell by pressing the plus button, and then I print out the value of x, I don't need to assign the value again in order to make sure that it prints out, in this instance, 10. So I run the cell, and again I get 10. What if in this cell I then added another 5? Well, that will take the current value of 10, increment it by 5, and then restore it in the variable x and print it out again. And so this will now print 15. If I run it again, it will print out 20. And again, it will print out 25. There are other operations that we can do with variables. There are a large number, but the key ones are addition. There's also subtraction, which does exactly what you expect it to. We'll subtract a value of 5 from the current value of the variable. We can also do arithmetic such as multiplication, which will give us 100. And we can do division. You have to be careful with integer division, right? Because it will return an integer, and you should play around with the Jupyter Notebook to see whether it gives us the lower value, or whether it rounds it up, or whether it rounds it down. This is something you should be able to work out for yourself. Finally, we can also have two asterisks, which mean raised to the power of. So this is the current value of x raised to the power of 5 and assigned to the value of x. And then the other thing that's very useful to be able to do is a percent sign, which is a modulo. Modulo returns us the remainder after having divided the first number by the second. So if the first number, if I say x is equal to, let's say 146, and I take modulo 12, well, I know that 144 is 12 times 12, so 146 is 12 times 12 plus 2, and so the answer should be 2. Again, you need to think about this carefully to understand exactly what the modulo operation will do. This seems like quite an esoteric operation to have, but in fact it's incredibly important within computing, because if you're looping through something many times and you want to, say, print out a value every 50th time, then that can be very easily done with a modulo operation. So if you want to do something every so many steps, that's often a trigger for using the modulo operation, and we will see that later on in the example. The second thing that I think is very worth stressing very early on in Python programming is the fact that Python has a huge number of modules. So as opposed to most things that you do in your degree, I would encourage, when learning computing, to cheat as much as possible. Use Google to try and work out if someone's done something for you before and copy how they did it. Similarly, you don't want to reinvent the wheel when it comes to doing complicated things, for instance, solving a set of linear equations or a differential equation, or optimizing some complicated function. Instead, there are lots of modules that people have worked out how to do something efficient for you already, and you can repurpose those programs that are written in a modular way so that you can then use them for your own purposes. You can even create libraries yourself, so you can have code written in one file, and then you can just import that file and use that functionality from a different file that was potentially written for a different purpose. So how do we use that functionality? Well, if we open a new code cell and we type in import NumPy. Now NumPy is a library that is distributed with most Python implementations that contains a lot of very powerful numerical linear algebra routines. So if we do that, that means that we've imported all of the functionality of NumPy into this notebook, and so we can use any of those routines at any point we want. Similarly, there are libraries such as math libraries that contain a lot of the standard mathematical operations that you may want, for instance, the trigonometric functions. So that can be imported as well. But remember, when you downloaded the original files from Keats, there was also a file called tutor.py, and this is also another module that we want to import. And the reason is that this tutor module that you will have with each of your sessions contains things that automatically can check for the results of your exercises that you will do in each of the sessions. So this allows you to be confident that you've got the right answer. So for instance, in the first exercise that you were asked to do, down here, this simple task asks you to calculate the volume of a sphere. The volume should be both printed out and stored in a variable called vol. The radius of the sphere is 2.5, but this should also be assigned to a variable since you may want to change it later. To check that you have the right answer, the tutor module should be imported if it hasn't been imported in the previously run cell, and the final line of the code cell that you run should be tutor.check, which will call the function check from the tutor module which has been imported. So let's try this exercise. Again, let's insert a new cell, and this will be a cell that we want to write this code in. Now the formula for the volume of a sphere is 4/3 pi r cubed, right? So let's set the radius equal to a variable that we will call r and set that equal to 2.5. We can then let the volume be assigned to the variable vol, as it suggests it should be, and we can let it equal to 3 times 3.14152, which is pi, times r cubed divided by 4. So the reason I did it in this way is because when you're writing mathematical expressions, you need to make sure that you obey the order of precedence that you normally have in algebra, right? So if I did this, then that would have, if I wrote the fourth, it should be 4/3. If I write this, then I would need to include brackets to make sure there was an unambiguous definition of the order of the operations. So this should be, this is an example of what the correct code could be, but you can use brackets in your expressions to make sure that you have the correct order of precedence that you want. Then we can run this. That hasn't actually printed anything out, so you don't expect any output. So in order to get the output we want to print the value contained within vol, and we also, as it suggests above, we want to get the tutor to be able to check that we get the right answer. We have already imported the tutor module, so it should remember and have access to all the routines in tutor. But just to make sure, we can import it again. So that will import the tutor module. So if we run this, it seems to work pretty well. It says pretty good, but still not exactly correct. The reason it's not exactly correct is because I'm using an approximation to pi here to 5 decimal places. Now that might be enough for your purposes, but remember, we should be able to do better, right? Now one thing that we could do is we could find in a book or online the value of pi to a larger number of decimal places, and we can substitute this expression for pi to higher accuracy and get a better answer. But that seems a bit laborious, and it's not really the philosophy of Python. Someone should have already done that for us. So I would recommend you go to Google and you type in Python. And the first thing that comes up is mathematical functions. So we can look through here and we can find pi. Right? These are lots of functions that are already calculated. Oh, and the constants here. Math.pi gives us the mathematical constant pi to all available precision. That sounds like what we want. Now to do this, we need to import a module. It's the math module. And we can give the name of the module. Then the dot indicates that there should be a constant or a function from that module that we can import. And then there is pi, which will give us the value that we want. So we've looked it up on Google, someone else has done it for us, we can use that within our session. So we want to import the math module here, and then instead of this approximate value of pi, we just want to put math.pi, and that's pi in Python to arbitrary precision. If we rerun this cell by pressing Shift and Enter again, we find the correct volume to all decimal places. The final exercise that we do is working with the Fibonacci sequence. The Fibonacci sequence is a sequence given here, whereby a current value of the Fibonacci sequence is equal to the sum of the previous two values. So this session is called Diving into Python because I really wanted to show that there was a real program that we could really get to and understand by the end of the first session. We will go through these sorts of things in more detail and try and explain in more detail the syntax exactly of these snippets of code. However, it should be easy enough to just read this code and understand what is going on. So in this example code, we can run it, and it gives a result of 4.6 million. So how is this done? We have three variables, x, y, and z. X denotes the two previous value in the Fibonacci sequence, y denotes the previous value, and z denotes the current value. And then we also have the result, because the result is what we want, which is the sum of the Fibonacci sequence whose values are less than 4 million and are even. So that's the plan. So we need to generate the Fibonacci sequence, we need to find the values that are less than 4 million, and we need to sum the even value terms. So this is one way to do this. It's not the most compact way in the world to do it, but it is certainly one way of doing it. We have x, y, and z, which denote three terms in the Fibonacci sequence, as I said. This is 2 before, this is 1 before, and this is the current value. Note that when you're looking through these snippets of text, it's possible as well to add comments to the text, which are things that you add to code blocks that the computer will completely ignore, and they can just be used to try and clarify what's going on. And these are denoted with the hash. So once you insert a hash, everything on the rest of that line will be ignored, but they can just be kind of aid memoirs for yourself when you return to the code. So I'm putting these in to try and clarify what's going on. So when I say current value, that doesn't really make any sense. What is the current value? Well, in order to generate this sequence, we want to loop through a part of the code many times, because we want to be able to systematically go through this sequence term by term. So to do that, we have this while statement here. This says while z, which is the current value, is less than 4 million, which is what we want to do, because we want to sum values that are less than 4 million. Okay, and after that, there's a colon, and then there's a block of code that's indented. And everything that's indented, it will be looped over until this condition is not satisfied anymore. So while z is less than 4 million, it will continue looping through this block of code. When it's larger than 4 million, it will exit this block of code and go on to print the value held in the variable result. So within this looped bit of code, the current value is given by the sum of the previous two values, which makes sense. It's how the Fibonacci sequence is defined. Then we come to this curious statement here. This says if z, which is the current value, modulo 2 equals 0. So this is what's called an if statement. This says that if the current value modulo 2 is 0, then we can execute the indented code within the if statement. Otherwise it doesn't, it just skips down to here. Now, as I said, this modulo returns us the remainder when you divide the value in z by the number 2. Now that will give us 0 whenever z is an integer multiple of 2, which is exactly what we want. We want the even valued terms. So this line here will execute whenever z is even. And when that is the case, it will take the variable result and it will add to it the value in z. So this makes sense from what we talked about in terms of the operations previously. So this is giving us the result that we want in terms of the sum of the even valued terms. And then finally, we need to move along the sequence. And this can be done by assigning the value currently in y to the variable x. And this will mean that what is currently the previous term will become in the next iteration the second previous term. Similarly, the current term, which is held in the variable z, will become the once previous term, the last term, which is held in the variable y. So you should think about this code and make sure that each line of it makes sense to you. This then, we then ask to print the result, and we get the value that we expect. We then ask to change this code a little bit. We want to copy this cell and modify it. So we do that by selecting it with the blue line down the left-hand side, pressing C for copy, and then V for paste. And we get another text cell that we can modify, but retain the original code for reference. So what it asks us to do is to sum all values of the Fibonacci sequence which are less than 400,000 and also integer multiples of both 3 and 8. And we can use a tutor.check to make sure that we get the right answer. So if we copy this tutor.check, that will make sure that we get the right answer. As it is at the moment, if we run the cell, we will get the wrong answer. So how do we modify this to get the right answer? Well, the first thing is that this while is looping over 4 million terms. We only want 400,000 terms, so we can just remove one of these zeros, and that should satisfy that criteria. The other thing is that we want to sum up the values which are integer multiples of both 3 and 8. So how can we do that? Well, if we change this modulo 2 to a modulo 3, that will make sure that this is only executed when z is an integer multiple of 3, because only then will the remainder, once you divide z by 3, be equal to 0. But we want 3 and 8. So the only way to do this, well, one of the ways to do this is to add another if statement inside the first if statement, so that it will only go through both of them if both of them are satisfied. So we do if z modulo 8 equals 0, then we need to indent this again, and this will only execute now, this result line will only be executed, and it will only be incremented by the value of z, the current value of the Fibonacci sequence, if both 3 and 8 are multiples of the current value z. So if we run this cell, the tutor will tell us that this is now the correct value. So hopefully this has given you a bit of insight into the things that you should have picked up and recapped the things that you learned in your first computational lab session. The only other thing to make sure is that you can save your notebook, so you can go back to it at a later date to make sure you understand what you've done, and that's why I would stress that you should feel free to add cells, add text, annotate these notes as much as you see fit, so that you understand what's going on. We can then do a file, close and halt. You can close the Jupyter tabs as your web browser, and then you can go back to the terminal where you executed the Jupyter kernel from, and you can just press Control C and press and shut down this notebook server by typing Y. Oh, no answer for 5 seconds yet. Just Control C and then Y, enter, shutdown confirmed, and then all should be fine. So I hope that enthused you into the power of computing. In subsequent sessions, we will go back and we will work through more pedagogically about exactly how to do loops systematically, how to do if statements, and build up to real physical applications. Furthermore, if you're already quite proficient at programming, you already have some experience, I would encourage you to look at the Ada Lovelace Computational First Year Physics Prize. More details of that are also on Keats. Thanks.